You should see my slides now, right?
Yes, we do. Yeah. So with that, I'll hand over to you. Thank you, Benjamin.
Yes, thanks, Stephen. So I use the title here, preCICE and exascale, to keep it simple. The exascale probably you have to put in quotation marks. So I'm not going to show exascale results in the presentation, but more want to explain a bit the parallelization concepts in preCICE as well. Yeah. I roughly organized this presentation in 3 parts. So first, I want to give you a more general overview of preCICE. And yeah, I will do this with a demo as well. Then in the second part, I'm going to talk about the parallelization concept of preCICE. And in the very end, I want to show you what we currently work on and what we want to work on in the next years. Okay, so let's start a bit with the general information. So preCICE is developed by 3 groups, 2 groups at the University of Stuttgart and 1 group at the Technical University of Munich. And you see most of the developers here on this slide. This is the big picture of preCICE. There's a lot of information on here, so I'm going to spend a bit of time to explain you that picture. Let's start here in the left top. So let's say you want to couple a CFD solver, for example, OpenFOAM, and you want to couple this solver to a FEM solver, let's say Phoenix, for fluid structure interaction. Then you can use preCICE for this, right? You have to make a difference here between different software packages. That's going to be important. So we always make a difference between the solver. Solver here would be OpenFOAM. Between an adapter. So adapter is kind of the glue code between the solver and the coupling. And the coupling itself, preCICE here is in green. preCICE is a library, right? So it has an API and you need to call it. So the whole coupling, we call this a library approach. The simulation calls the coupling. And this calling happens typically from the adapter. And the adapter now can have very different shapes depending on the solvers. So often this is again kind of a standalone software package. For example, again, a library. So the solver calls the adapter and the adapter calls preCICE. preCICE comes with a number of ready-to-use adapters. So basically for the codes that are listed here below. So for OpenFOAM, SU2, for a number of finite element packages. But you can also develop your own adapter. You can couple your in-house code, and then you directly call the preCICE API, which is available in these languages here. So what actually does preCICE do? This is depicted here in the middle. So these things preCICE does, and so this is executed within the green boxes here. So for example, preCICE communicates data, right? So this solver might run on a different node on a compute cluster than this solver. So preCICE communicates data. preCICE maps data between different meshes. For example, with projection mappings as depicted here on the picture, or also with radial basis function interpolation. preCICE executes coupling schemes. So what is a coupling scheme? So first, this is the pure logic of who has to send data to whom and when. So we there differentiate between explicit coupling, so you only couple once per time step, or an implicit coupling, you sub-iterate in every time step until convergence. But it's not only this logic. In here, there are also acceleration methods. So for example, quasi-Newton acceleration methods for implicit coupling schemes so that you really get a stable coupling here. And something we currently work on is time interpolation. Good. So far a bit the big picture. Now I want to show you a quick demo. So here you see two terminals, and both terminals are at the same location right now, almost. Now they are at the same location. And what is in this folder here? So this is one of the tutorials that you can run with preCICE. We have two subfolders here, one for an OpenFOAM case and one for a Phoenix case. And we want to couple OpenFOAM with Phoenix here. There's this file preCICE config. I'm going to show you this file a bit later. In here, we specify how we want to do the coupling. So I'll step into the OpenFOAM directory here. And if you inspect this, this is pretty much a normal OpenFOAM case. So if you're familiar with OpenFOAM, maybe, so these are all kind of OpenFOAM config files. One special file here is the preCICE dictionary. I'm going to show you in a minute. And here on the other side, I'm going to step into the Phoenix case. And here again, this is pretty simple. This is one Python code, a Phoenix application code, and also again, a configuration file for preCICE that we're going to use. And now we can couple these two by using this run scripts here. So what is in the run script? This is very simple. So here we basically only call this this Phoenix code. So let's do this. We run the Python script. In the Python script, we use our Phoenix preCICE adapter, and the Phoenix preCICE adapter then calls preCICE, and we see here output from preCICE, and in the end tells it is waiting to set up the communication to the coupling partner. So for this, we now also run OpenFOAM, and OpenFOAM starts, and now you see that both simulations run, and they're exchanging data, and you have a coupled simulation. So while this runs, I want to show you some of the files. So here on the Phoenix side, we had this Python script, and in the Python script here, you import Phoenix preCICE, which is the adapter between Phoenix and preCICE. And then, we always try in the adapters to speak kind of the language of the codes that we want to couple. So if you jump here, we initialize here the adapter, and then you can, for example, create a coupling expression. And this coupling expression is just a normal Phoenix expression that you can use, for example, as a boundary condition for Phoenix here. Okay, so I guess if you know Phoenix, you understand what I mean. If you're not so familiar with Phoenix, then maybe ignore this part. And very similar on the OpenFOAM side. Also here, the adapter is a library. And this is in the, this is more an OpenFOAM specific thing. In the system control dict, this is an OpenFOAM configuration file. You can specify function objects that should be loaded at runtime. And here we just specify that we want to load the preCICE adapter, which is again here a shared library. Okay, and then on top, we had this preCICE configuration file, which is an XML file. In here, we define what kind of meshes we want to use for the coupling, what kind of codes we want to couple. We have a fluid code here, the OpenFOAM code, and a solid code. I do not want to explain details here, but maybe interesting. So we use here the communication. We do here with what we call sockets. So technically, this is TCP/IP. there are different backends that you can use. You could also use MPI here for the communication. And in order to establish the communication, there needs to be kind of one initial token, and that one needs to be exchanged via the file system. So we need kind of a shared directory for both solvers, which we specify here. Okay, let's see how far we are. Yes, so simulation is done. If you want to visualize now, you can, for example, do this with ParaView. And both simulations exported VTK files, and you can just load the VTK files or VTU here. So this is the Phoenix run, and then you jump to the OpenFOAM side. There you have this .openfoam file. And for example, let's directly jump to the end and look at the temperature. Okay, yeah, this is a very simple scenario here. You have fluid flow here on top, and this here is like a solid domain, and you get heat conduction here, and here convection and conduction. You can also visualize the meshes here to really see, okay, we also use different meshes here, and preCICE maps at the coupling interface. It maps between the different meshes. All right. So far the demo. Let's jump back to the slides. Yes, now it's a little bit of time to brag a bit. I don't want to spend too much time here because you can also read online most of the things, but just to mention a few things quickly. So preCICE has a quite extensive user documentation. It's written on Markdown and rendered on our website. But recently we also implemented a way to convert this into a PDF. And then the PDF currently has more than 250 pages, only user documentation. Yeah, they're ready to use adapters. This I already told you, the API. preCICE has a quite vivid community. We exchange ideas in chat, and there's also a forum for preCICE. It is currently used in more than 100 research groups in academia, but also in industry. preCICE is a member of the Extreme Scale Scientific Software Development Kit. So this is kind of a bundle of software packages maintained by the national labs in the US, which all the software packages can be built with spec and can be kind of shipped together. And this is kind of pre-installed on more and more supercomputers, which is very nice for us. So also preCICE is installed, pre-installed on more and more supercomputers. We invest quite some work in our CI and our testing infrastructure. So we have tests on various levels. So from unit to integration to bindings to adapters to system tests. If you're interested in details for all of these things, you find more on the website of preCICE or in our recent reference paper from this year, where there is a preprint online already. Good. So much about the general introduction. Now I want to talk about parallelization. And for this, I want to mention that preCICE was also funded by an exascale program, kind of a sibling program of ExCALIBUR, which was called SPPEXA. Has had a bit a different focus than ExCALIBUR, I think. Also, it's already in the past. It was the German priority program on software for exascale computing. So it was not on hardware, was purely on software. Was running for 6 years. 17 projects, each with 4 to 5 PIs and 1 PhD student per PI. So I guess kind of, if I extrapolate a bit the funding, I think half of the size of ExCALIBUR. One of the projects was the ExaFSA project, where we looked at fluid structure acoustic interaction. And within this project, we pushed preCICE towards exascale. yeah, disclaimer, not every part of preCICE is ready for exascale yet, but we really did a lot of the parallelization work within this project. If you're interested about SPPEXA, here the website, and if you're interested in what we did here with preCICE, in this paper here, this was after the first phase of the project. We kind of summarized most of the parallelization work that we did in preCICE, and which I also want to quickly outline now. All the parallelization starts at the point that preCICE works with static coupling meshes. Means that coupling meshes, so the meshes that you use to exchange data, they are defined only once during the initialization, and they're normally not changed during the simulation. This is a bit of restriction, but also makes a few things much simpler. And it is not a problem for many coupled problems. So you can already do with this fluid structure interaction if your fluid solver works in the ALE framework. So if you have moving meshes in the fluid domain, if you want to couple particle meshes and you have a fixed background mesh for your particle method, and many other applications. But of course, it also has some restrictions. So what you cannot do is to work with many immersed boundary methods. You cannot work with solvers that have dynamically adaptive meshes, or for example, particle methods without a background mesh. Maybe important to know, so we are currently working to generalize this to allow dynamic meshes in preCICE, but this is currently work in progress. So what does this now mean when we talk about parallelization? So this means that we can compute many things already during the initialization. So the complete data mapping and the complete communication pattern, we only compute once during the initialization. That means that the initialization can become expensive. We can also afford this as long as it does not become too expensive. So it should still be tolerable. But then the effort per time step is really negligible. So the coupling is then much cheaper than the solver themselves, and therefore the complete coupled setup is highly scalable. And the coupling sometimes here is even embarrassingly parallel, depending on what methods you use in preCICE. Okay, and then also important to know, to understand is that we use a peer-to-peer approach. So maybe you have seen this picture. So this is one of the standard FSI benchmarks. You have an elastic beam here, and you have a fluid around. And what you see here are kind of the domain decomposition of the two domains. So the solid here is decomposed on 7 domains, and the fluid on a few more domains. And let's say these are our solid ranks, and these are our fluid ranks. Now, peer-to-peer means that we use a direct communication here. There's not like an instance here sitting in the middle that does the coupling. So we don't have any central server-like entity, and we only communicate data where we need to communicate data. So for example, this solid rank here only communicates data to the 4 neighboring fluid ranks. The coupling numerics, so for example, the data mapping or the quasi-Newton acceleration, we then also directly compute on these ranks. So for example, if the data mapping is computed here on the solid participant, we compute it on these ranks here. And this makes the approach very, gives us a very good scalability per time step. So let's look at an example. This is already a bit older, from 2016. Here we took like a cubic domain where we solve the Euler equations, and we have a density pulse that travels from one side here to the other side. And now we do an artificial cut of the domain and we couple the two domains, and we are interested in the scalability. We use here a discontinuous Galerking solver named Atelis from the University of Siegen with many degrees of freedom so that we get a good, strong scalability here. In preCICE, we do a nearest neighbor mapping and we handle the communication. And we run here on the, already a system which is not longer in operation today. But we compared here a bit the scalability of the monolithic simulation. So if you only run this in one Atelis instance, or what happens if you couple two. And in orange here is the monolithic run. In the dark blue, there is the coupled one. And in the light blue, there's kind of an older concept that we had in preCICE based on a server-based parallelization concept. And we do a strong scaling here. And you see, it nicely scales. And there's no visible overhead here between the monolithic run and the coupled run. Whereas the old concept here was really not suitable for such parallel runs. We took the same example and made it a bit bigger. So on this slide here, only two things changed, and the number of degrees of freedom. Now this is one order of magnitude bigger, and kind of the number of cores that we run on. And now we only look at the complete coupled simulation. That's the blue line here, and the orange line is the costs of the coupling. And you see that the coupling is much cheaper than the simulation itself. And this way, the coupling does not interfere with the scalability of the simulation, right? Only, if you go further at some point, we might run into a problem here. Okay, so this was the time per time step. Interesting to see is what we do during the initialization. So this is a bit the costly part. And the main concept here is if you want to couple two solvers, A and B, they both have their meshes, MA and MB, and they both define kind of their own domain decomposition implicitly by just defining where their meshes are, giving this information to preCICE. And now in order to set up the coupling, what preCICE does is it computes the data mapping and the communication pattern. And this happens by sending one of the two meshes to the other participant and repartitioning there. So in the end, we have this setup here, solver A and B. And for example, the mesh MB now is on both ranks, on both solvers. And we can use this now to map data on participant A between the two meshes and communicate data over the mesh data structure of MB. So during the initialization, what we have to do is we need to bring this mesh here to the other side and repartition it here again. And I'm running a bit short in time, so I'm gonna only scratch a bit the surface how we do this. We do this with a two-level approach. On the first level, we only handle bounding box data. So on the one side, we collect bounding boxes around the partitions. We give those to the other solver, and the other solver also has bounding boxes around its mesh. And then by comparing the different bounding boxes, we can filter out a preliminary communication pattern. And then we use this preliminary communication pattern on the second level to exchange the actual mesh data structures. And this we can then really do in a point-to-point way, fully parallel. If you're interested in the details, so this is work we published this year, explained in this paper here. We again did scalability studies. So this now is a weak scalability for, again, a kind of an artificial test case 1,000 vertices per MPI rank. I cut it short a bit. So the dark blue here is the overall initialization time. Ideally, this should be constant, right? In a weak scalability, it is not constant. So we still have a few problems. But maybe important to know is also the overall time here. So even with a rather large case here, we are still kind of in the range of minutes. So in 5 minutes here, we can initialize the case, which is tolerable here as you only have to do it once. And this here are the CPU cores, only the CPU cores that handle the coupling. So if you do a surface coupling, then it could also be that your case is even much larger, and these 12,000 ranks here would be at the coupling interface. All right. What are we planning? What are we doing right now? Where do we want to go in the next years? So originally, preCICE was developed for low-order mesh-based surface-coupled problems. So typical example is fluid structure interaction. Right now and in the coming years, we want to kind of extend this. So we are working on data mapping for mixed dimensional problems, solver-based higher order data mapping, partition of unity RBF data mapping, support of dynamic adaptive meshes, this I already mentioned, waveform relaxation to handle multi-rate coupling, volume coupling, mesh particle coupling, and macro-micro coupling. Yes, if you're interested in any of the details, please let me know. I'm happy to tell you more. Jumping over this and coming to the end. So again, a bit an overview of the main concepts of preCICE. So it's a library approach, it's a peer-to-peer approach, and this makes it very scalable. A few links may be interesting. We have our third user workshop in February, fully online. Check out the website if you want to join. With this, thank you for listening, and I'm happy to answer questions.
Thank you, Benjamin. And I can we've got a question in the Q&A, but before we go to that, if anybody has any questions for Benjamin, we do have 5 minutes. So if you could either put them into the Q&A, or if you'd like to raise your virtual hand, I can enable you to speak if you prefer to go that way. So whilst we're waiting, Ben has 2 questions. So Ben Rogers has asked, firstly, do you need to write a new adapter for each software?
Yes, which is some initial effort. So we already have a few adapters that you can use off the shelf. If you want to couple your own code, well, you have to call the preCICE API. You can do this kind of directly in your code. This is probably the first step that you do. If you want to have it a bit more flexible software-wise, you would want to make this an own software piece to separate concerns.
Okay, thank you. And Ben's second question, can you tell us about dynamic load balancing?
Yes, so something we don't do right now, right? So we with the static meshes, we kind of we expect that the 2 solvers can handle their own load balancing, right? If it's dynamic, then currently you would have to restart the complete thing if you change things. This is something we're currently working on to make this also kind of part of the API, that you can also tell preCICE, okay, now my coupling mesh changed, here's the new mesh, please reinitialize. Maybe interesting for load balancing. So something preCICE also supports is parallel coupling, meaning that you can run your solvers at the same time. So you can run your fluid and your solid solver, for example, simultaneously, and you can also get kind of a load balancing between your coupled solvers this way.
Thank you. So from Dylan Rabini, so with preCICE, it's not possible to use it to couple stationary and rotating meshes. That's with a question mark.
Yeah, depends on how you treat the rotation, right? So if you have a way to kind of map this back to the original geometry, so if you have in your solver kind of a mapping between the rotating part and the stationary part, then you can still couple it with preCICE. So we have users that do something like this.
Okay, thank you. So from Hamza Sadar, could you use preCICE to couple OpenFOAM to PyTorch with a trained model in inference mode?
Yes, that's an interesting question. So I think technically, yes, it depends on what model you learned and how you do kind of how you couple the equations exactly, right? You can call preCICE has Python bindings, right? So you can call it from a Python script, and the coupling with OpenFOAM is there, right? I think it depends. It's more a question of how you what your learned model looks like and how you exactly want to couple the equations.
Okay, thank you. And from Karim Ali, do the coupled softwares move in time similarly, or can we allow a solver to move with faster time steps, for example, in CHT timescales of the fluid part, where it's much smaller than with the solid part?
Yes, so technically this is already possible now, that you can use different time step sizes, and then you couple only every fixed time window. Currently, we kind of do this in a naive way, so you kind of lose your convergence order in time. But we are currently working on waveform relaxation methods, so that you can also have a higher order representation in time that you can sample from, and then you can even do this without losing your temporal convergence order in your codes.
Okay, thank you. Garth has his hand up.
Yes, thanks, Stephen. Thanks very much, Benjamin. That was really very interesting. I was wondering, could you speculate on what issues there might be, or perhaps there are no issues, if you're in a heterogeneous compute environment? So you've got one of your libraries might be running on a GPU, the other on the CPU, or even if they're both running on the GPU. Have you looked at what particular challenges there might be in that case?
So we had a few use cases that did such things, but then they always did the coupling on the CPU, right? So you have code A is running on the CPU, code B is kind of handling the coupling on the CPU and doing the numerics on the GPU, right? And so this works technically. I think the biggest challenge here is really then you need to bring efficiently the data between CPU and GPU in this part of the code, right? Currently, you cannot directly call preCICE from the GPU. If maybe this is kind of low order data, so that it's only like a small amount of data, then I think it's no problem at all. If it's large data, then you need to find an efficient way already in your code to handle this. Yeah.
Okay. Okay, one more question's coming. Well, I'll read this one out, but then if anybody has any further questions for Benjamin, please do type them into the Q&A. Just make sure it's obvious that it's specifically for him, and he'll be able to answer those by actually typing an answer as we go. But the final question is from Chris Goddard. So for fluid-to-fluid coupling, so for example, two different CFD codes, is the coupling at the domain, boundary, or can it handle overlapping domains?
You can do overlapping domain. So for preCICE, no problem at all, right? You just have to give a different domain to preCICE, right? A different mesh. like our adapters currently do not all support this yet, but this could be extended, I think, rather easily in the adapters, so that you kind of, for the adapter would be kind of a volume coupling, but only on parts of the domain, kind of a small layer of cells close to the boundary. Yes, so it is possible, but needs a little bit of work. Yeah.
Okay, thank you. Okay, given the time, I think I'll probably call it a day with the questions. So thank you again, Benjamin. It was a very interesting talk as always.
Thanks.
And